Okay, let's dive right into this explainer. If you've ever stared at a massive spreadsheet full of survey results or test scores and just felt completely overwhelmingly lost, well, you're definitely in the right place. Today, we're going to learn how to tame that chaos. We're breaking down the chapter on the fundamental techniques used in statistics to organize raw data. Because once we do that, the data actually makes sense, and we can use it to uncover real truths about the world around us. So let's get into it. Here's our roadmap for today. We're going to hit 5 main stops. First, taming raw data chaos. Second, 4 distinct ways to classify that data. Third, understanding statistical variables. Fourth, building frequency distributions. And finally, dissecting the anatomy of a class. Let's get moving. Starting right off with Section 1, Taming Raw Data Chaos, bringing order to the unclassified. To really grasp this, think about a local junk dealer or kabadiwala. Imagine him buying up old newspapers, broken glass, plastics, metals, you name it. Now, if all this junk is just thrown into a massive, disorganized pile in the middle of his shop, it's utter chaos. Managing his trade would be virtually impossible. To actually survive and run his business, he has to group the junk. He ties up the newspapers, he sacks the glass bottles, and heaps the metals in their own specific corner. By grouping similar items together based on the market for reused goods, he brings order to the chaos. And you know, we do the exact same thing in our daily lives. Just like trying to find a specific history book is nearly impossible on a completely cluttered desk, finding a specific piece of information in a sea of raw data is incredibly tedious. But when you arrange your books onto perfectly structured library shelves, maybe sorting them by subject, finding what you need literally takes seconds. Analyzing data requires us to organize it into neat, predictable shelves first. Otherwise, the entire purpose of even gathering the data is totally lost. So here is the absolute crucial point. Raw data is completely unworkable in its original state. Think about the Indian census, which contacts over 1 billion people. If you just had a list of 1 billion unsorted responses, there is no way you could conclude anything from that. Raw data is highly disorganized, extremely large, and incredibly cumbersome. We literally have to summarize and group similar characteristics together just to pull out the story that's hidden within those numbers. That brings us to Section 2, 4 ways to classify, specifically by time, space, quality, and quantity. First up, we have chronological classification, which is organizing data by time. For instance, we can track India's population growth decade by decade, plotting values for 1951, 71, 91, and 2011. Grouping data by years, quarters, months, or even weeks classifies it chronologically, and this creates what we in the biz often call a time series. Alternatively, we can use spatial classification. So instead of time, we group our numbers by geographical locations. Imagine comparing the yield of wheat in kilograms per hectare across different countries like Canada, China, France, Germany, India, and Pakistan. Whether it's countries, states, cities, or districts, if the grouping criteria is location-based, you're looking at a spatial classification. Then we have the last 2 methods, which essentially separate the non-measurable traits from the measurable ones. Qualitative classification deals with attributes, things you just cannot measure with a number, like gender, nationality, or marital status. You group the data based on the presence or the absence of that attribute. On the flip side, quantitative classification deals with characteristics that are explicitly numerical. We're talking height, weight, age, or maybe a student's marks on a math test. Moving on to Section 3, understanding statistical variables and how data actually varies. To really master quantitative classification, we need to look at the first type of variable, the continuous variable. A continuous variable is smooth. It can take any numerical value within a range, including exact fractions and decimals. Think about the height of a student. As a student grows from, say, 90 centimeters to 150 centimeters, they don't just teleport from one whole number to the next, right? They physically pass through 90.85 centimeters, 102.34 centimeters, and every conceivable fractional measurement in between without skipping a beat. It has infinite gradations. Conversely, a discrete variable acts entirely differently. Why? Because it only takes very specific values. Its value changes by making finite jumps. It completely ignores all those tiny intermediate values between the jumps.
It literally leaps from one value to another, completely unable to land anywhere in the middle, just like a person jumping from step to step on a staircase. Think about the number of students in a classroom. You can have 25 students, or you can have 26 students, but you can never ever have 25 and a half students. The variable jumps directly from 25 to 26, completely skipping all the fractional values in between. When we compare them directly, it's super clear. Continuous variables slide along a scale smoothly, capturing every micromeasurement, while discrete variables leap from step to step. Now here's a really quick pro tip. Discrete variables aren't only whole numbers. A variable that jumps from 1/8 to 1/16 to 1/32 without taking the values in between is actually still discrete because of its jumping nature. All right, section 4, building frequency distributions, constructing the categories.
This right here is our absolute ultimate solution to the raw data chaos we talked about earlier, the frequency distribution. It takes an overwhelming, disorganized list of numbers, like the test scores of 100 different students, and groups them into structured classes. It shows us exactly how the values of our variable are distributed across the board. To build one of these, we methodically answer 5 interlinked questions. First, do we need equal or unequal sized class intervals? We usually use equal sizes unless our data has a massive, extreme range, like daily incomes ranging from 0 to millions. Second, how many classes do we actually need? Usually somewhere between 6 and 15 is the sweet spot. Third, what's the size of each class? Fourth, what are the strict limits? And finally, step 5, we tally up and get the frequencies. When we do this, 100 messy, individual math test scores immediately become an easy-to-read trend. Our classes sit clearly on one side, ranges like 0 to 10, 10 to 20, and 20 to 30, while the actual frequency, the number of students, falls on the other. Instantly, a teacher can see that the highest concentration of scores is right smack in the middle, with 23 students scoring between 50 and 60. The chaos, completely gone. And that brings us to our final stop, section 5, the anatomy of a class, breaking down the boundaries. To read our new distribution correctly, we have to dissect these classes. Every single class in our distribution is bounded by 2 distinct ends, called class limits. The lowest value is the lower class limit, and the highest value is the upper class limit. So for example, if we look at a class of 60 to 70, 60 is the lower limit, and 70 is the upper limit. The physical distance between them, which you find by just subtracting the lower limit from the upper limit, is called the class interval, or class width. In this case, the width is exactly 10. So, the crucial takeaway here is that the class frequency represents the actual count of observations sitting comfortably within those strict limits. If our raw data has the numbers 30, 32, 34, 35, 37, and 39, well, all of those specific values fall into the 30 to 40 class. That would give us a class frequency of 6. But guys, here is where the real magic of statistical organization happens. Once we group our data into these classes, we actually drop the individual observations entirely. We don't use the specific scores like 32 or 37 anymore. Instead, we use the class midpoint or class mark. You find it by simply adding the upper and lower limits and dividing by 2. So for the 10 to 20 class, the midpoint is 15. Going forward, we solely rely on this mathematical midpoint to represent the entire class for all our future calculations. It's a huge time saver. As the chapter we're covering sums it up, the purpose of classifying raw data is to bring order in them so that they can be subjected to further statistical analysis easily. That perfectly wraps up our journey today. By understanding continuous versus discrete variables and by mastering the frequency distribution, we've essentially acted just like that junk dealer. We've taken a room full of useless, scattered clutter and turned it into a neatly sorted, easily readable system that is fully ready for real, impactful statistical work. So, I'm going to leave you with a challenge. Look around your own room right now. Find the chaos and try to classify the world around you. Think about the actual temperature of the room you're sitting in. Is it continuous or discrete? What about the number of books on your shelf? Organizing data isn't just some boring chore for statisticians. It is exactly how we make sense of our surroundings. Thanks so much for joining me on this explainer, and keep looking for the order within the chaos.